So regarding the lab situation, looks like Wednesday would be okay for a bunch of people. So I'm going to check with 105 to see if we really can move to their Wednesday slot. But it looks like Tuesday, Wednesday would be a reasonable combination. So if there are people who really cannot make either Tuesday or Wednesday, please let me know in the next, today, so that we can try to figure something out. But it looks like everybody could. It was just a matter of what they prefer. OK, so as I said, we're going to post the homework number 2 in the afternoon. And we'll post the solutions. Alberto, did you send the solutions already to Kali? OK, so let's do that so you guys can take a look before homework 1 evaporates from your head, kind of see what the solutions are and maybe ask some questions about it. So last time we finished up the bipolars. We did both the behavior of the device and then looked at the biasing, then looked at the small signal circuits, and then looked at sort of common single stage configurations. I omitted one, which was common base. And you have it on the homework, so or some variant of it. I think the 240A people will have it on the homework. Again, there will be separation for 240A versus 140. If 140 students want to do the 240A part of the homework, we're not gonna say, we can grade it as well. It's more for your practice, right? So, but for 240A people, it's something that comes into the overall score. So today, we're going to move on to MOSFETs and go through sort of basic device physics review and hopefully ramp up to small signal models if we can. So in homework 2, you're going to be using kind of both the biasing equations, but also small signal models for MOSFETs and bipolars interchangeably. So that's kind of for this week. I'll also have a makeup lecture for Wednesday, likely on Monday evening, 2:47, or this classroom, and I'll post that on Piazza and announce it also on Monday in class. So just to have it in mind. People who miss it will be able to hopefully look it up on webcast. OK, so let's dive into the MOSFETs here. And really, MOSFET stands for kind of metal oxide semiconductor field effect transistor. And unlike kind of the name, the first thing we're going to try to do is to understand intuitively what's happening in the FET is we're going to look at the MOS capacitor, which is kind of a more primitive element that we can construct circuits. And it looks something like this. So I have this sandwich on top, which is the gate. I'm going to pretend here it's metal, just because it's easier. Okay. And then, or maybe we can just do this. I'm going to have here, I'll call body, or B. And this is going to be silicon p-type, so very lightly doped silicon. And this layer over here is going to be SiO2, or silicon dioxide. Now, this is something that we would call NMOS capacitor. And N here, you may be confused. It's not from this P. It's just from the type of charge that accumulates right here underneath the oxide surface, and therefore kind of makes the device to behave as a capacitor. And we'll see kind of in different regimes what that charge is. and how it affects the capacitance and the behavior of the FET. Now, I said I'm going to pretend this is metal. In reality, in modern processes, well, actually, in modern processes, it is now metal. It used to be that it was polysilicon down to sort of 32 nanometer node. It was very heavily silicided polysilicon, so metallized polysilicon, just to be able to better match the work function to the underlying material. And you'll see how that plays later when we really go and derive the threshold for the FET. But in modern processes, like from 32 on, like Intel's using hafnium as a metal kind of gate to be able to better control the charge in the channel. So if we take a look at this gate and then plot the charge concentrations, which is kind of what we're all interested about, if I label this thing as sort of the x-axis starting from, let's say, coordinate 0, and I then plot the charge, so I'll say charge density here as a function of x, then if I have the gate as positive, I'll have some charge in the metal after sort of this is Tox, the oxide thickness. And then I'll label that as sort of something like QM. It's greater than 0. And then what is going to start happening on the p-type side is, since it's p-type, I have a lot of acceptors. Right? So these acceptors are going to grab an electron that's floating around, and they're going to create these ions. They're negative. They're sitting right here. And these are up to some depletion depth, xd. Right, so what we're going to have here is the charge density on that side would look pretty uniform because I'm doing kind of a uniform doping of acceptors. And that charge density will be due to acceptors. And we're going to call this like QB. Right? QB is charge in the body, and it has to be less than 0. Now, these two will be kind of matched in area. I didn't draw it quite nicely. Let me maybe nicer. So that we have sort of a net field across. Now, if we take a look at the various levels as VG goes through different voltage values, let's take a look at what happens with these concentrations. So I'm going to try to draw this on sort of a slightly different scale. One is sort of the axis is going to be VG. This is my regimes of operation. And then on Y, I'm going to draw capacitance. Okay. So capacitance is essentially proportional to charge and inversely proportional to voltage, right? So through that, we'll be able to kind of see what's really happening in the device itself. So when VG is positive, then we have essentially that we have plus here, which is this charge over here, and then we have our negative acceptors on the other side, right? And because depletion region is kind of getting bigger as my VG increases, my capacitance is kind of going to start going down. And the reason is that now all of a sudden I have this whole region across my plates of the capacitor exist, right? So they exist on one side here, and then on the other side, kind of, or where the end of the depletion region is. So my capacitance drops, and I'll call this region sort of depletion. On the other side, if VG goes negative, then if I look at the cross-section again, this is gate. This is PSI. So if I start lining up negative charge here, what is going to trickle up? What do I have a lot in this P-type silicon? I have a lot of mobile holes, right? So these holes are going to trickle all up and line up right at the surface here. Okay. So I'm going to have a situation where, in terms of my charge density, I have my negative now. But then I also have a matching holes density on this other side. And it's a very narrow, because I can slap all the holes like right next to the surface, right? And because of that, my effective width of the capacitor is actually narrower, right? So my capacitance is higher. So that shows like as being the capacitance in this region. We're going to call this accumulation. Okay. And that kind of, once they get slapped over here, there's really no change. I changed the voltage. There's just more charge, essentially. But my capacitance value doesn't change, right? Now, the interesting thing starts happening on this side where as I'm increasing the positive voltage, the depletion region expands, but does that very weakly, right? If you recall the equation for the depletion region is kind of a square root dependence on voltage, right? So it's very slow after a while. Okay. But there is one phenomenon that we learned with bipolars about the base behavior, and that's that the minority charge, and we'll label it as NS. The minority charge in this material, in p-type, is what? Electrons, right? So this minority charge is actually proportional to the exponent of the surface voltage. Right? In base, we had this situation that at NP of 0 was e to the VB over VT. And so here is the same. It's going to be some surface potential over VT. Right? Which means if we're increasing this gate voltage, it's true that the number of depletion ions get more exposed because the depletion region grows. But it grows very, very slowly. Whereas this exponential grows very quickly. So after a certain point, which we'll call the onset of inversion, we're going to start getting a lot of electrons to just go and rush to the surface. Right? And so what we're going to have in inversion is, so this is accumulation. In inversion, we're going to have the opposite thing, right, where we have our gate charge. But in inversion, we're going to, and we had our slowly growing, this was depletion charge. And now, all of a sudden, we're going to get something that is this part of charge. And this is inversion charge. Okay. And these are acceptor. So depletion charge will be bare acceptors, right? They're ions. But inversion charge will be minority electrons that rush to the surface because their concentration exponentially depends on the surface potential at the oxide. Right? And at some point for high enough VG, that exponential will be much, much bigger than what the acceptors have. And so we're going to call this point a threshold. A threshold, which is the onset for inversion. And this whole region here, we're going to call, well, let's sketch it a little bit better.
start climbing up. I'm going to sort of define it rather kind of at the top point. Okay. Okay, so, and then this region is called inversion. We're not going to go immediately and derive this threshold voltage. I just want to give you sort of an intuitive feel of where it comes from, and how this charge dynamics is changing within the capacitor. And then we're going to use that all kind of the surface potential work functions to kind of derive this number. But for now, it's just how the carriers are moving around. Okay. Oops, that got to be the last page for some reason. Okay, so maybe just one more thing here is that we call this accumulation. This is inversion. There is sort of weak inversion happening on this edge, and then this is depletion. But we're going to sort of, for all intents and purposes, really not talk too much about weak inversion operation. Okay. So what we would like to do is kind of then derive a simplistic model, because we're, after all, circuits folks, for that charge or the capacitor that we have. And we can use then this to be able to figure out what's really happening when I actually go and add source and drain and make this to be a transistor. So let's draw something that will go along that way. So we have our sandwich, which is the metal gate, and then the oxide. And then we're going to add two pieces to it. This is our base, or body. This is going to be N+, and this is going to be N+. These are another two regions that are doped, highly doped with the donors. And this is going to be source, and this is going to be drain. And so we're going to assume that we're in this region where with the VG is greater, is kind of increasing, and we've already went into the region where we started getting these small electrons here underneath the surface. And because we have now these two other terminals, which are source and drain, these kind of electrons will form sort of a bridge between source and drain. And that's why we're going to call them channel. Okay. And then what we're going to do is calculate, so they present mobile charge in the transistor, because these electrons are minority carriers. They move around. Okay? They're pinned to this surface by the positive potential, but they move around. And so they can potentially carry current if they move around. So we want to figure out what is that current under different biasing conditions. So to do that, we're going to say that we're going to define QM, which will be mobile charge in the channel. Now notice this mobile charge, so acceptors are not mobile charge. Only these minority carriers that get attracted to the surface are the mobile charge. And we're going to say that QM equals 0 when VG equals V threshold. Right? So at the point where we were kind of on the onset of inversion, we're saying we don't really have this mobile charge. It's just essentially getting formed after the threshold voltage. Okay. And then we'll have that QM of VG is, if we sort of use the capacitor model, is going to be some capacitance times any excess voltage on top of the threshold. So as we start inverting and attracting the electrons, we know there's 0 of them at threshold, but anything after that will contribute to the charge. And so that must be then Vg minus V threshold. Okay. So if we add, in this case where we added source and drain, now we're going to refer this Vg to some point along between source and drain. And because we've added source and drain and potentially have different voltages at source and drain, the potential in the channel will be also changing. So what we need to do is let's say define some coordinates here. We had previously x that is gone from 0 to here. And now, because we're interested in transport of electrons from one region to another, from source to drain, then we're going to essentially have also this coordinate, which is going to be the y. So let's see what happens here. I'll do the grounding of the source terminal, and then I'll apply some voltage VDS on the drain terminal. And I'll also ground the body just for now, so that I don't confuse things too much further. So in this situation, I can write the equation for the mobile charge as a function of the coordinate where in the channel this is. So for example, at this spot over here. And it will be Cox prime. Cox prime is essentially the unit the capacitance. So this is the, let's call it from 0 to this point L. L is called the channel length. It's the total distance from the edge of the source to the edge of the drain. And then in this dimension right into the screen, we have the W of or the width of the transistor. Right? So Cox prime is going to be the capacitance per unit length. Right? So I'm going to have Cox prime times W, and then if I integrate this along L, I will then get my total charge. Right? So this is kind of the capacitance of this strip right here that I'm looking at. Okay, so that is equal to VGS minus V of Y minus V threshold. So why did I write this here? If you take a look, if there is some potential between source and drain, right, all these points over here are not going to be at the same potential. Right? They're at the same potential only if drain is also at 0. Right? But if drain is not at 0, there will be some field across here that will be changing the potential. And so at this point, for example, I will have the extra potential V of Y on top of what the gate dictates. And that will affect what is my total charge that is attracted to that point. What are the total number of electrons that are attracted to this point? In our normal capacitor, I didn't really have this lateral field that was changing the potential. I just had the gate that was controlling the inversion. But here I have this extra factor. And we'll see this is the extra factor that causes kind of the current to, or the electrons to move across from source to drain. So if I go and look at the mobility of the carriers or the electrons that go through the channel, this will be sort of the speed or the velocity. This is the electron velocity. Will be dy over dt. That's just how much I get across the channel in a unit of time. And then that is actually defined as the mobility of electrons times the field, the electric field at this point y. This is mobility of electrons at surface. The reason why it's at the surface is because as electron is gliding and there's oxide, it's kind of bouncing around. It's not as clear as if it was going completely through just crystalline silicon, right? So there's some degradation in mobility because of that edge boundary effects. But this is just a sort of a secondary thing for you to remember. And then we have the field is going to essentially be a derivative of our potential over y. Now, one thing to note here is that we're assuming that this mobility is kind of constant. It will actually depend on the voltages we apply. But this is kind of called sort of velocity saturation. And we're not going to talk about that today too much. But right now, we're assuming that this mobility is kind of a constant. So now that we have this, let's take a look how to derive the current. The current is really just flow of electrons, right? So if I look at the current, the charge times the speed, I should be getting my flow, right? So that's what I'm going to do. So I'm going to say Qm of y times Vd of y. So I'm looking at the velocity of electrons at a certain coordinate, and I'm looking at the number of electrons that are moving at that velocity, and that's my current. Now, this current is flowing only in one direction, from source to drain, so it's not going anywhere, so I know that current is constant across every slice. Notice that the current is constant, but these two quantities can change just to maintain the constant level. And so what we can do is then write it out. We're going to replace the expression for Vd and then expression for the charge prime. And then we're going to have Vgs minus V of y minus V threshold. OK, maybe I'll just delete this for now. Okay, and then the other thing that I have is from this expression, I have dv of y of d of y. Now, what I can do with this, I can integrate this from 0 to L in the y dimension, right? So dy. And on one side, what I'm going to do get is essentially id dy from 0 to L. And then on the other side, I can do the swap, because I know that at 0, my voltage is 0. My V of y is 0. And then at L, my V of y is VDS. Okay, so I'm going to do sort of a variable swap. So I'm then going to write it as, OK, let's take the constant out, mu n w c ox prime. And then I'll just write it as 0 to VDS instead of 0 to L. And then again have VGS minus V minus V threshold dV. OK. So from here, ID, this is ID times L, so I'll just divide with L. And then from here, essentially, we get VGS minus VTH times, OK, let's sort it out nicely. So VGS minus VDS over 2 minus VTH, and then times another VDS. Okay. So if we nicely write this out, this is then mu n w c ox prime over L. And then here we're going to have VGS minus VTH times VDS minus VDS square over 2. Okay. Okay, and this is what we would call a formula in the linear region. we did all this without assuming that this voltage is anything like spectacularly high. We assumed that the charge exists all along the channel, right? Because that's when we did this integration over here, right? Now we're going to see that that only happens in this so-called linear regime. When we move into the next regime, which is saturation, this is no longer the case. So in saturation, what's really happening if you draw the transistor as this voltage if this is, let's say, grounded and VG is high enough, then there is plenty of inversion of electrons on this side of the channel because the gate to source potential, this potential over here, the field is pretty big, right? So there's a lot of electrons that get attracted here. And now, as you're moving toward this side, what's happening is that this potential over here, which is dictated by the influence of the drain, if drain is increasing, then at some point you get the so-called pinch off. And that is that at this very point over here, there isn't any more charge that is being inverted. There are no more electrons that are sort of attracted from the P substrate. Okay, so this is called pinch off. Now, what is the condition for this pinch off to happen? It's the onset of inversion, right? So what's the condition for the inversion? Yeah, so something has to be threshold, right? So which potential has to be equal to the threshold voltage? Which two terminals sort of dictate what's happening at this point? Okay, so VG minus V. D, right? So if in other words, if VGD is equal to V threshold, then this is pinch off, or onset of saturation. So after this, if I increase my VD further, I just essentially start depleting even more. So this starts pulling back, but it's weak because now it's kind of a depletion region forming there as well. Okay, and we're going to do that as well. But this is kind of the onset of that behavior where drain stops having influence on what's happening in the channel. Okay. And we sort of want that, right? If you remember bipolars, in forward active region, the collector didn't really have much influence on the current of the collector, right? And so this is kind of similar now. After the onset of saturation, my drain is not going to have as much influence on the drain current as it had in the linear region. Okay, so I can reformulate this by essentially adding this potential of everything referring to source. So I have, in this case, that VG equals V threshold plus VD, or VGS is equal to V threshold plus VDS. Or I can rewrite this that VDS is equal to VGS minus V threshold. So if I go and draw the curves for the drain current, as the function of VDS. Normally, I'll get behavior like this. And if I look at the formula that I showed you for linear region, it would look something like this. Okay? But this line over here, which says that VGD equals V threshold, or that VDS equals VGS minus V threshold. If I plug in this condition back into the formula for my current, what I'm going to get is that ID equals K prime W over L times, and then I'm going to have VGS minus V threshold square minus VGS minus V threshold squared over 2. So that's K prime W over L times VGS minus V threshold squared over 2. But I did this on this condition that VDS equals VGS minus VT. So this will be VDS square over 2. And this is what is called ID sat. So if you look at this, it's essentially a square depends on the square of the drain source voltage, and that's really this curve over here. So this curve marks the boundary between linear region and the saturation region for the transistor. Right? So everything here will be linear region, and everything over here will be saturation. In saturation, we should start expecting that the transistor current is independent, is no longer obeying this parabola law. It's now sort of independent of VDS. Okay. So let's go ahead and calculate that a little bit. So we have our profile for the transistor. And we said that there's going to be kind of this charge profile, which is the channel. And then this is L. And depending on kind of the potential of the drain, you may get a little shrinkage here. Let me do a different color. You may kind of terminate earlier. And so this length will be L effective. So the E field will then depend on that length. So we're going to say that E equals sort of VGS minus V threshold over LF. Or ID sat equals ID of VGS minus VTH equals VDS. Okay, and that was essentially what we just derived. Now, in practice, we have that ID sat really depends on this L effective, not just the full L as the channel is being pinched off. So we're going to write it as K prime over 2 W over L effective times VGS minus V threshold squared. And this effect we're going to call channel length modulation. So how do I basically go and figure out what really the effect of this L effective is? So if you remember, we had sort of a similar effect of this modulation in the bipolar transistor. Can anybody recall where that was happening? In the base, right? So what was causing the base width to modulate? Yeah, so the voltage that the voltage at the base collector junction was causing that depletion width to change and to shrink the effective base width, right? But what caused that voltage to change? If you look at the overall transistor, I have only 3 terminals to move. What can cause that internal base collector potential to move? When transistor was on, we said VBE was pretty much 0.7. So whatever you do to other terminals, it stays like that, right? So all the voltage drop gets dropped across base collector. So if I change the collector voltage, most of the voltage drop is across base collector, right? And that's what's causing it to move. So here, similarly, if I'm increasing VD, I'm going to be getting a lot of field across that junction, and then I'm going to be pinching the channel more. And so this L effective will decrease. And so I can model that by looking at a change in ID as a change in this VDS voltage, right? And so if I look at the previous formula that we had over here, the only thing that really could potentially depend on VDS is this L effective, right? And so we're going to figure out how that is. So if we take the derivative, it will be minus K prime over 2, and then WL effective square, because we really were taking derivative with respect to L effective. And then times VGS minus V threshold squared times, of course, the derivative of L effective with respect to VDS. Right? And from here, this piece is essentially, together with 1 L effective, is essentially ID. So minus, okay, let's do it. Minus ID over L effective times DL effective over dVDS. Now, if you look at this picture over here, this was L effective, but it was retreating back because this piece here was the increase in the depletion of this drain. If I increase VD, the depletion region into the P, because this is highly doped, nothing really happens on the drain side. Most of the depletion region forms on the, yeah?
So along those lines, why does the current stay constant? Why doesn't the current go down if you...
So the question is why, if you basically don't have any charge here from the inversion, why does the current get why does the current still flow, right? Well, notice that the current, okay, we had it on the previous one. The current was kind of the charge times the velocity, right? So in the pinch-off region, it's a very small region. You get essentially a very high velocity crossing it because there's a lot of field applied, right? But I only kind of do this integration for the time that there is actually a charge. Yeah, so if this number is very big, then this number is, even though it's very small, I'm still getting sort of constant current. Okay, so the bottom line is that this XD really is equal to L minus L effective. Okay? And when we use that fact here, then again, I can write this as ID over L effective times this delta L effective will really be minus XD, delta XD. So I'll just write it as delta XD over del VDS. So now this is something that's familiar. It's kind of a change in depletion region versus the voltage that gets applied on that junction. Right? So we know that was like a square root kind of dependence of the depletion region with the VDS. Right? That's standard for any type of junction. So we can now define something that's kind of very similar to what's happening in bipolars, and that's we'll call it also VA, like early voltage, which is the ID divided by delta ID over delta VDS. So we're just taking this ID and this delta ID over the slope of ID versus VDS and defining that a voltage that we extrapolate to as the slope. So this then goes just from the expressions to delta VDS to the minus 1. Okay. And then if you look at the normal FETs, these values are somewhere between 20 and 200 volts, roughly. And then we can again, so this is kind of same as early voltage. And we can then again define sort of lambda as 1 over VA. And that will give us, again, this slope with which the ID changes, just very similar to what was happening in the collector on the bipolar side. So our final modified equation for the saturation would be K prime W over L times VGS minus VTH squared times 1 plus lambda VDS. Okay. So this will be the saturation. And then remember what we had in linear region was something like this. So when I go and now draw the curves to incorporate all of these effects that we talked about, I'm going to draw ID over VDS. And first thing I can draw is kind of the boundary, which is this quadratic. And the quadratic will say that ID sat equals K prime W over L or of 2L times VDS squared. So I'm going to draw that curve. And then in this region, I have pieces like, okay, let me just draw this. Then I have this early voltage, and I know that from here, I'm going to be getting some slopes. And then my curves will essentially go like parabolas till their points, depending on the linear equations in the linear region. And then they're going to, instead of sort of flattening out or going down, which is for linear, now we're in saturation, they're going to start following these lines, right? So and here. Okay. So those are going to be my transistor curves of drain current versus the voltage. And of course, each one of these will be for a certain VGS. This is VGS2, VGS3, and obviously this one is bigger than this one and bigger than that one. Okay, so now that we sort of looked at these things, let's spend, okay, we're kind of running out of time. Okay, so I guess we'll stop here and then finish up the threshold and the small signal models next lecture. But you got sort of the intuition about how the channel gets formed and that it does depend on some threshold voltage. We're now going to just see which kind of exact expressions, Fermi levels, work functions come into play here. Okay. There's still some problems that you can try to attack with this biasing and the conditions that we did today that are in the homework for CMOS. And of course, everything that's bipolar is easy. If you want to look ahead and read a little bit in the chapter about CMOS signal models, that's okay as well.